Hey all, hope you all are doing good. So welcome back to the first chapter after the last video where we introduced what all we are going to cover in the next upcoming weeks, that is 6 weeks. So today what we are going to do is we are going to learn about the LLM basics, and then we are going to understand about the transformer architecture, and as a dependency flow we are going to learn about tokenization and embedding. So we are going to cover the first three heading today, and in the coming section we'll do the continuation on the attention piece. Okay, now one disclaimer I want to mention that the first two sessions is mostly about the maths. We will do some practicals, we will see how the flow is happening behind the scenes. We will try to understand the big picture, but at any point of time if you are not able to understand, don't worry, because after the two sessions we'll completely work on the frameworks and will use the libraries and etc. So these two sessions, if you are able to understand, well and good. If you are not, don't worry. So with that mentioned, let's jump on today's content. So welcome to the understanding of large language models and transformers. So the first thing that we are going to see is in general how we use ChatGPT. First, let's write down a statement and then let's see the response and then let's try to visualize it. So let's say I am going to write pizza is tasty. Okay, so what I gave here is few words. Okay, now how did the GPT or how did the LLM interpreted it? What is it? Let's try to understand that in the deep. So at the end of the video we will understand how these words are coming out. Okay, and yeah, with that mentioned, let's see. So if you see the flow inside the LLM, as soon as you enter the prompt, what happened was, let me bring both the screen here. So if you can see, what happened first is I entered pizza is tasty, right? I entered three words. Okay, so the sentences that we are writing, it doesn't understand it, in the sense the machine, the system, the GPT, the LLM doesn't understand it. So the very first step that it does is it tokenizes it. So in our understanding, let's say tokenizes means pizza is tasty. We have three words. So pizza is one word, is one word, tasty is one word. So for our understanding, let's say this is three tokens. Okay, but for the machines, it could be PIZ is one token, ZA is second token, IS is third token, a space is one more token, and tasty can be like T can be one token, A can be one token, S can be one token. So that's how it divides. But for our full course we will uh, take the slide and we'll try to run on this assumption that pizza is one token, is one token, tasty is one token. So it's nothing but a words, right? So that is called tokenization, dividing the sentence into a smaller chunks that a machine can understand is called tokenization. We will spend some time on tokenization and its algorithm in a minute, but let's understand the full flow. So the very next step is embedding. So as soon as we think of embedding, what do we come into picture? That you are putting something and you're plotting it somewhere. Okay, so what is embedding in LLM is the token that it generated. Okay, we can see it is PIZZA, but internally what tokenization does is it converts it into the numbers and plots it into the a space, a vector space. So we will try to understand what is embedding again in few more minutes, but overall it plots it. For example, when we say maps, we talk about longitude and latitude about a point because we are talking in two dimension. But similarly, we can talk about three dimension, four dimension, which we are going to see. But as of now, the step one is embedding, that is dividing it into words, then converting it into numbers, and then embedding, what it does is it plots into a vector space, let's say three dimensional. For our understanding, a maps is a two dimensional. Now once this plotting is done, okay, it's random, let's say it's wrong, it is wrong because it doesn't know where is Hyderabad, where is Telangana, or where is New York. It doesn't know, it simply plotted it randomly somewhere. Now all these states will communicate with each other saying, hey, I'm here, oh, you are there, I think we should meet here. So some kinds of communication will happen, and that is where we call it as an attention. So the matrix, the maths behind it we will understand, but that is where we call it as attention. Now as an output of the attention, now we have correctly plotted where is Hyderabad, where is New York. Okay, where is Kanyakumari, where is Jammu and Kashmir, everything we plotted correctly as part of the attention. Now then unembedding is saying the statements, okay, the output that is generated. Let's say pizza is tasty from underscore place, so that underscore it needs to predict. So based on this complete plotting, it will predict the next word, and to convert that uh, what I can say, the latitude or longitude or the numbers into the words, we call unembedding. So embedding means plotting the words into the space. Unembedding means converting that bullet from the space into the words, and that's how the next word is predicted. So don't worry if you didn't get it anywhere. We will deep dive into each of them in next few moments. So with that mentioned, what do you think our first topic will be? Of course, it's tokenization. So if you see here, yeah, before we go into the tokenization deeply, so this is the flow. We understood what happens when we search, what is the LLM doing, but in this complete flow, which part is input, which part is output, which part is LLM. Okay, and for our reference, right, by the definition, LLM and GPT, let's say both are same. Okay, so the tokenizer IDs, that is words converting into numbers, will call it as an input. Okay, that is not LLM. So who will do tokenization? Will it be done by GPT or LLM? No, it will be a separate algorithm. So that tokenizer IDs will be an input to our LLM, and this LLM will be doing the plotting and then sending it to attention layer, where the corrections will be happen, the points will be moving from one direction to the other. We will see in that in depth, and then finally converting it into a words, predicting the next word or next song, or giving you the essay of your thing will happen unembedding. Finally the output is what we will be showing, we see in this output is shown, right? So how it has happened, basically it got the output saying that 1 comma 2 comma 3 comma 4 is the correct output in the space. But when you unembed it, you understand that 1 comma 2 comma 3 comma 4 is nothing but a word called absolutely, and that's how we see it on the output. So you understood which part is LLM, which part is input, which part is output. All right, so I'll just take one more minute on it. So what is GPT? What is the full form of it? So GPT stands for generative pre-trained transfer. Okay, where generative is the one where the text is generated. Um, so it's based on what? So pre-trained, it's based on the data that we feed in, on which it learns, and then generative pre-trained model. So this finally, sorry, generative pre-trained transfer. Now finally transfer is where the transformer comes into picture, which is where we will say how input is converted into the output. It is basically a big neural network. If you don't know what is neural network, that is fine. You can just assume it's one of the machine learning model just for the understanding sake, but that's what the GPT is. Okay, now why we are calling it as LLM? It's basically because it is very large. Of course it is very large, and language model, so it's a ML model, and it's very large. Why we will say very large, we will see, we will understand by the end of this session. Because whenever we are talking about a GPT level of thing, whenever we are calling large language models, we are talking about 10,000, 20,000 dimensions. We are talking about 20,000, 30,000, 40,000 matrices. So that's why we call it very large language models. All right, so with that mention, let's um, move on. Yeah. So how does the text becomes a number? So step one, the text is divided into tokens, and the tokens is given in IDs, and then IDs is plotted into the vector space. Why we are calling vector space? Because when you plot Hyderabad and a New York, you are not only plotting the points, but you are also plotting that if you want to go to New York from Hyderabad, what is the direction of it? So we are talking about the vector. Okay, then we keep attention layer so that the plotting is done correctly. I don't want to plot Hyderabad in Australia, so that's where attention layers come in. And then we have an MLP layers, and finally we understand what is unembedding and what does softmax do, we will see. But MLP, unembedding and softmax is, the whole purpose is to generate the next word or predict. Okay, so this you can take up, you can pause the video, see each, this is a GIF, you can see each step. And with that mention, let's move on. So if you see, we have discussed previously that Tokenization, let's say pizza is one token, is one token, tasty is one token. But it is in terms of machine, when we say unbelievable, it's not one token. UN could be one token, believe could be one token, able could be one token. Now you can see this unbelievable is given its own index, its own plots. Okay, so we will see how this tokenization can be done. Now it can be done with various algorithms. Few of the things is BEP, it's encoding based and then word piece. So why this we have so many algorithms, because the way we want to give a big dictionary to as an input, the way we want it to tokenize it's basically different based on different criteria. It does the tokenization. For example, BEP does tokenization based on the frequency of occurrence of characters. So if I give you a corresponding example, when you talk about sorting, you have why you have so many algorithms, quick sort, bubble sort. It at the end it does the same, but the way it does, the approach is different. That's why we have multiple algorithms for tokenization, and we will do practical on two algorithms of tokenization. Again, I'm repeating, this is the maths behind what is happening LLM. So if you are not understanding, that is completely fine. You can just keep a blank mind, listen to what I'm saying, capture whatever you are able to, and move on to the next video. I'm sure that by the end of this playlist you will become a professional. So with that mentioned, hold out to your horses and we will move to the practical. So we are going to do the tokenization using two algorithms. First is BPE, which is byte pair encoding. So we will not go to okay, let me zoom in a bit. I hope this is visible now. So I'm not going to explain each of them. I will put it in my GitHub link, and you can find that GitHub link in the description, and we can have a separate session to understand in depth about this. But I'm just executing this, and this is the corpus that we are going to learn. And you can see the statements that we have given, that is this list of words. It did the tokenization like this. So pizza is divided into one token, pizzas is divided into one token, pineapple divided into multiple tokens. Pi is one, n is one, ea is one. So and le plus the ending character is also one. Unbelievable is completely into one token. So you see there is a difference. You cannot simply say that it will take this as one word as one token, but that is what we will assume and proceed for our next steps. And how it did what it did, it's not part of this scope. Similarly, word piece. So if I run this, I'm not going to explain this as of now. So you can see pizza is divided into one token, pizzas is divided into one token. For the next four, it is not able to tokenize at all. It means it is not able to divide it. It is not considering that itself as a one word. Now we can understand why it is doing that, why it is saying unknown, if we understand how it works. But as of now, my whole purpose is to say there are n number of different tokenization algorithms, and if you know any other or you want to suggest, do mention in the comment section. But that's the intention. Now I hope you understood the tokenization. Now we will see that when we are talking about GPT-3, why we are talking about GPT-3, we want to understand the scale at which the models that we are using are working. So we understand that pizza is tasty is my complete dictionary. In that, from a human perspective, the dictionary has only three words. But GPT-3 is trained on a vocabulary of 50,257 tokens. So this includes 50,257 words? No, it includes apostrophe, the curly braces, the spaces, all the special characters, numbers, everything together. It is 50,257. Okay, so I hope we are able to correlate how the tokenization is happening in our perspective versus the scale at which GPT-3 is operating. All right, so we understood tokenization. Now, how we will do the embedding, what plot we will do in the vector space. To understand that, here I'm taking an example of four words. So I've taken four words: man, woman, king, queen. So first of all, every word like pizza is needs to be plotted, means it needs to have its own coordinates. So when we talk about map, we will talk about two coordinates, that is latitude and longitude, because that is sufficient. But when let's say we are talking about my community, okay, you can say I am on the third house on the fourth floor, but as the complexity increases, we include more dimension. Like, am I on the third house, fifth floor of A block, B block, C block, right? And then I can include one more dimension if we are talking at a major scale, like is it in north direction, south direction, east direction, west direction. So based on the complexity, the number of dimension will increase, or we would want to increase it. Okay. uh, all right, so with this context, let's move on to our example. So let's say now we are talking about 5 dimensions. You can see dimension 1, dimension 2, dimension 3, dimension 4, dimension 5. Now if I want to plot Hyderabad on the map, I need two dimensions, which is sufficient. But in our case, we are dealing with 5 dimensions. So the coordinates of man is this. Now you can say how you got it. Okay, so at any point of time when we are working with it, the model will start with let's say it's a random value. Okay, once it passes through the attention, once it gets the context of the complete book or the complete paragraph or the complete data set that we are giving it, then it will correct its values. So we will talk about that later, don't worry. As of now, that questions you keep it aside or keep it in the comment section. As of now, our intention is how the embedding is happening. So let's say man has these 5 coordinates, woman has these 5 coordinates, king has these 5 coordinates, queen has these 5 coordinates. So this is called embedding matrix. Okay, what is embedding matrix? The dimensions will be your column, your each token, I won't say a word, your each token will be your row. So when I want to know the plotting of the woman, I will pick up all the dimensions of the second row, like you can see I'm highlighting here. Okay, now if I want to find where is it in the vector space, I would simply search with these coordinates in the vector space. Okay, it will be multiple dimensions, right? It will be rotating. So we can imagine maybe up to 3 and 4 dimension, but 5 dimension, 6 dimension, 20,000 dimension, we cannot imagine. But I hope you're getting the gist. Okay, now if you see here, the token ID of woman is what? 2. So for our understanding, starting the IDs from 1 and not 0. So here the token ID of woman is 2. What is the vector of woman? So it is the full row, 2093153 1.12. I hope you understand how we are reading it. So every token will have a vector. Okay, and that vector is nothing but an array of all the dimension coordinates. Okay, I hope you understand what we did. So first we took a word, then we tokenized it and generated the ID for it, and then we got the vector which we are plotting in the multi-dimensional space, which we are calling it as embedding. Okay, so if you are getting it, fine. If you are not getting it, it's okay. You can you can view the video once again. If not, it's okay, no problem. So here in 2 dimensional, I can plot it like this. Okay, woman is here, man is here, king is here, queen is. This is just a demonstrator purpose, that once I have a vector, I can plot it in 2 dimension or any dimension. But for the visualization, I kept 2 dimensions. Okay, so yeah, and let's say I'll give you one example. King is here, man is here, woman is here. Okay, but queen is here. So do you think that's correct? If men and women are at one places, then king and queen should also be at one place. So that's what attention layers help us. Oh, man is to woman, king is to queen. So why king and queen are in different locations? It should be closer. So that's what attention layer, back propagation, feed forward layer, all these are the layers in MLP layers. All these layers are there in the neural networks, which we'll understand slowly. I hope you are clear with tokenization and embedding and what all things are involved in the LLM so far. Any questions so far, do mention in the comment section, and let's move on to the next slide. Yeah, so let's say now you have plotted. Okay, and what we did, we moved from a matrix to a vector space where we did the plotting. But what if I found a point in the vector space? Now I want to read it in the embedding matrix. So basically you have the coordinates. Now you want to find what is a token ID, or you want to find where is that word or token in my embedded matrix. That is called lookup. So how would I know? So each token ID is used to look up a row in the embedding matrix. So here, for example, this one, what is our vocabulary size? It is 4. Okay, what is our embedding dimension? It is 5. So our embedding matrix shape would be 4 cross 5. Okay, so if you want to grab a word called woman, you can simply go into your embedding matrix and you can look up for the token ID 2 and you can get its corresponding points. Okay, so that's how we use embedding matrix as a lookup table. Okay, now if I compare this embedding matrix with that of the GPT matrix, I mean GPT's embedding matrix, I should not say it is a GPT, but it is the embedding matrix of the GPT. You can see you have nearly how many vocabulary? 50,257, if you can see here, right? And similarly, what is a dimension? So if you can see, it is 12,288 dimensions. Do you understand what is the, how many weights or how many values are we dealing with? So just to give one more line about this, when you're talking about machine learning model, what is it? It's basically some kind of structure or some kind of neural network that you are preparing with the tunable parameters. Means, hey, Hyderabad and New York are in wrong places, so you should modify a weight, you should modify a toggle, you should adjust some switch so that it both the location points correctly. So what do we call this thing? Is called weights. This is called tunable parameters. Okay, so all the weights will help us the attention layer. So when we say this is wrong, what is the adjust we will do? We'll adjust the tunable parameters and finally we'll bring it to correct. So that is what done as part of our full training, our not our training, the machine learning model training or neural network training, saying that okay, now the training is done. When we say training is done, what is the meaning of it? It means the tunable parameters, the weights that are involved to predict your next word, to do your next star, is now in correct position. Means when I say map is ready, it means now you can go from any place to any other place, because with the help of tunable parameters or all the positions on the maps are now correct. So it's ready for you to use. Now you can predict, oh, I'm in Hyderabad, now I want to go to New York because it is having this many this much distance. Or we can add one more dimension called traffic. We can say this much distance, this much traffic, so this is the amount of time that it will take. So that's when I say map is ready, it means all my tunable parameters are in correct shape now. Okay, so yeah, so here the matrix shape would be 50,257 into 12,288, which is nearly 0.65 billion. Okay, and just to give you an example, let me go to a last slide for a minute. So what I will do, we will come here. um, yeah, let me go here. uh, uh, no, no, no. Okay, I am going to a last slide where I want to share that how many total. So we understood, right? 12,288 into 50,257 weights is what embedding matrix is. Similarly, we will be having 50,000 into 256 into 12,288. That is, first we have dimensions into vocabulary. Now we have vocab into dimension during unembedding. So words to numbers is one matrix, numbers to words is one another matrix. So these many tunable parameters we have already dealt with. So this is 0.6 billion weights, this is 0.6 billion weights, total 1.2 billion weights. We understood that this is the matrix involved. But attention layers, okay, projection layers, MLP layers will have many more matrices. So total we will be having 175 billion tunable parameters. Just imagine the scale. So that is the amount of weights and tunable parameters that we will be understanding. So these metrics we will learn as part of next video, which is attention. But as of now, let's come back to what we were discussing. uh, all right, so I think we are clear with the comparison of embedding matrix with GPT-3. And if you see, okay, how you know that king and queen are related? How you know the chef and let's say Tendulkar is related? So there should be some algorithms, right? So we will talk about cosine. So uh, and if I take you to a secondary standard where you discussed about the scalar and vector, so what is the difference? I think every one of us know that scalar is only talking about the magnitude. It's only talking about the distance, the value, but vector talks about the distance. Okay, so here what we are doing is, you can see man is to woman, but king is to queen. So how we can say these are similar? If I know that men and women are similar in one POV, okay, so if men and women are similar in one POV, what is the result of the king? Okay, the answer should be queen. So how it will understand? So we should find what is the similarity between men and women. Let's say the answer is 226. So I need to find with the king plus 226, what is the word I will be getting? It should be queen, right? That's how we understand the similarity between. Okay, so let's take an example. A dot B, it's basically a dot product that I'm doing, and then again I'm doing A B multiplication below. So what I'm doing, first I'm multiplying along with the direction, and below I'm multiplying without the direction. So what is left? The multiplication result above, the multiplication result below is gone. So the only thing I am left with is direction. So cosine similarity is going to help me with telling that how similar these two words that are A and B are. So let's understand with few example. The range will be from -1 to 1. Okay, what is +1? It means they are exactly same direction. It means very similar meaning. Example, king and queen, when vector form a very small angle, means there is some variation but minute ones, approximately 1. So when it is approximately 1 means they are related. Okay, when it is orthogonal means it's a 0, the cosine is 0. Okay, it's 0 means it's unrelated. So if I say king and dong, the cosine should be 0. Similarly, if I say opposite direction means opposite meaning, so this will be 180 degrees. Hot and cold, the cosine would be -1, means they are related but in exactly opposite direction. Okay, so these are some of the example, and this was the analogy I was talking about. So king is to queen, how will I get it? So from king I would subtract man and add woman, I should get queen. Okay, so what is the purpose? What are we talking about similarity? Okay, so this similarity is helpful when I give an input to LLM, I give a context to LLM and say predict my next word. Okay, so if I give an example, one last example before I move to the next topic, which is why does it need this? So for example, if I say a model, okay, whether it's a machine learning model, whether it's some tree model, whether it's a fashion model, or it's about a model that students are building in the college, what is a model that you are talking about? So it should know the context, it should know which direction it should move, it should know what is the similarity I should measure it with. Okay, that's where the dot products, multiplication of matrices, all that will come into picture. Okay, so if you didn't get it, I would request you watch it once again or mention the questions in the comment section. If not, just relax. It's okay if you don't get it. You can continue with the next part of the video and next series. Definitely, once you complete and you come back, you will understand. I have that guarantee. I give you that guarantee. Okay, with that mentioned, let's move on to the next one. So why does it matter? You can see we are doing embedding. Why does it matter? So if you see, okay, this is how previously it is. So when I say this is my embedding matrix and I told you, how would you know what value, what coordinate I should give to a pizza? How would you know what coordinate I should give to Hyderabad? So you will get some random value. You will say give some dummy value. Okay, and we will understand two things. One, when you say that you are going to teach it, you are going to correct it, you are going to prepare a finalized map which everyone can use it, how you are going to do? Are you going to give a big data set, or when I'm using ChatGPT I will give only my words, right? And how is it, the pre-trained model or what? So we'll take two examples. In both of the examples you can see it, we are starting with an embedding matrix with random coordinates. Okay, and that random coordinates is random in both. Okay, you can see word to vec is one algorithm, and transformer, that is the NLM, the our context, is one algorithm. Okay, not, I would not say algorithm, one kind of flow. Okay, so in word to vec we are using context based cluster. So based on a different way of similarity, it will segregate and say which cluster it should common word. Okay, so here they are working with a cluster 3 and they are segregating, but if they want 10 cluster they can segregate. Okay, so what low level of clustering or how much concrete result you want, based on that you will give the number of cluster, and word to vec will divide it into the clusters based on various inputs and various criterias, and that's how clusters are formed. Okay, but in case of transformer we will be making use of attention. Previously we were using clusters, we are giving the numbers explicitly, and that's how word to vec was doing. And as part of our LLM flow we will be making use of attention, which will talk, we'll talk about back propagation, MLP layers and all those things, but as an output of the attention layer it understands that where is the correct plotting of each token, and that's how the segregation is saying, and we are saying you are good to predict the next word. Okay, so whether LLM or regular, uh, we need to plot it correctly and say the model is ready to be used. Okay, so that is why embedding matters. So I hope it is clear, and let's move on to the next one. So if you see this slide we won't spend much time. This is basically the two algorithms that we saw previously. What is the behavior and what are the steps involved, and all the details I've kept here, so you can pause, you can give it a read, and I will keep this deck in the GitHub as well, so I won't spend much time on it. All right. um, yeah, so if we understood, right, there is a cosine as one of the example. We understood it gives us that it is correct, it is wrong, it is a correct direction, it is opposite direction, it is not related at all. But there are many other things are involved, so I will talk about one loss function and we will understand why it is useful, and that's how we have many alternatives as well. So this loss function is saying basically that hey, these two are related, but with the loss of, let's say, I'll use all the, let's say I'll not use jargons, let's say these two are related by 80%. Okay, so there is an error rate of 20%. Okay, so if it wants to predict, okay, so let's say for a king there are two words, queen and princess. Okay, but when we are saying men is to women, what is more related? For king, queen is also related, for king, princess is also related, but the loss function would say as per the context given. Okay, because if I say man to daughter, then the relativity of king would be princess. Okay, let me come back to the statement one. When we are talking about man is to woman, what is the expected for king? It is queen, right? But we know that if I apply cosine algorithm, king is related to queen also, king is related to princess also. But with what loss, with what strength? So I would say in this POV, king is related to queen by 70%, or let's say 80%. King is related to princess with 50%. Okay, and when we are saying this, based on what? Based on the context, that is man is to woman. Okay, so error function will say that it is relative but only by this much. Okay, so we have the magnitude provided by cosine saying -1 to 1 range, and then we have this error ratio to support it. Okay, and yeah, that was just one example, but when I take minus to daughter, my expected result with the cosine and the error function is saying that king is to princess. Okay, now I won't go more into this algorithms which is out of the scope. But yeah, if you want a dedicated sections on the all the loss functions, gradient functions, and similarity algorithms, okay, just let me know in the comment sections and we will have one. Okay, so we will see, and it's all as part of training. Okay, so now let's see the Python practical of how the embedding looks like, and how we can say with the cosine how one is related to others. Okay, so for that let's jump on to 2 minutes for a Python notebook. Okay, so if you see here, I have given a random um, vector IDs or token IDs to king, queen, man, woman, chef in a proper way, so that our explanation does make sense. Okay, so let me create this embedding matrix, and then I would define the cosine similarity algorithms, so we are good with this. And then we are not going to talk about the code, but what I am going to say here, I am giving you the queen. Okay, and tell me how far king is related to queen, queen is related to queen, man is related to queen, and each are related to queen. Okay, so when I run this, you can see what is most related to queen. It is king, and then next it is women, maybe based on gender, and then it is related to men, and finally it's not much related to chef. You can see the value 0.32. Okay, so the prediction would be thin. Here we are just trying to showcase that how embeddings are used to understand which is related to what using a cosine algorithm. Okay, this is just one example. Okay, I think it is pretty much clear. So far, any queries between embedding, tokens, vectors, why embedding matters, the scale at which GPT works, cosine algorithm, loss function, traffics, training, loss, all that. If you have any query, to mention in the comment section. And then let's move on to the next one. So here, I think this we discuss that how, what is the level at which, the GPT's embedding matrices. So this is fine. And here is the thing. So it has this embedding parameters, basically embedding matrix has basically 617 million parameters, which is basically 0.6 billion. Okay, so if we see, we have talked about unembedding, okay, where we are converting the bullets to the word. Okay, so there the dimension will be opposite. Okay, here it was um, uh, the words into dimensions. In the unembedding it will be inverted, that is dimension into words. Okay, so yeah, and then think of embedding. Yeah, basically unembedding is the exit door where we are going to get the output, and you can see embedding goes through the transformers layers, and finally with the unembedding we get the output. Okay, so the multiplication dot products, and how the words talk to each other, all that we will see in the attention session, which is the next session. But I think you got the gist of what we are trying to see. And today we understood that we have 1.2 billion parameters just in the embedding and unembedding, and we have to uncover all this stats of other matrices as well. Okay, so finally, quiz time. This one I kept convention only here itself. But pause the video, read this question. Don't search on the Google. Just based on understanding, mention in the comment section what do you think is the answer of this and what do you think is the alternate of this. Okay. All right. And finally, the summary. So, in the beginning of this lecture, we understood what all steps are involved, that is tokenization, then it goes to embedding, and then attention talks to each other. Finally, MLP layers and attention gives us the next word for the prediction. I want to give you one statement here. So when we are saying next token prediction, it means it's a one word, right? Then how the big paragraphs, big essays are generated? Is it like the complete loop goes on again and again? For example, pizza is was the initial input. After prediction, we say pizza is very. After one more prediction, we say pizza is very tasty. So is the sentence passed to our model every time, and then for each time a word is generated? What do you think? Let me know in the comment section, because that's something we will uncover after the attention session. But do mention in the comments if you know. Okay, now let's spend 1 minute on understanding this mapping in our neural nets. So if you see, pizza is tasty was our input. Okay, then it gets tokenized and it is sent into attention layer, and this is how the neural networks looks like for the people who don't know what is neural network. And in the description I will put a playlist of my machine learning playlist. Who wants to know about the deep learning, the maths behind the neural network, and a bit more of ML and data science and deep learning piece, can refer that and come here. But who doesn't want to, it's okay. Attention is a neural nets as we see, and then once attention is done, feed forward is happening. Now it's not that the data will flow from attention to feed forward. It will be forward backward, that kind of multiple jargons we will use later, but that's how it happens. And finally the prediction happens. Now I want to tell you one more thing before I wrap up today's session. If you see, the image is not perfect, the second image, it looks like it's a bit cropped, right? So each word that we are saying is a token. Similarly, when we are talking about image, each pixel or each array of pixel is one token. When we are talking about voice, let's say a group of bullets is one token. Similarly, video, maybe a few layers is one token. So in everything there is a token, but for our understanding we are considering word for our learning purpose. Okay, now here the image is cropped because maybe while I made GPT to generate this image for your information. So while GPT was generating it, it was limited to this context. Okay, so when I give it the input that it seems it is cropped and you need to generate a bit more, then it will go back into this complete flow, and it understand that I need to increase or I need to see something else and get something more into my context and um, work. So context is again a matrix. See, every word that we are speaking is a matrix. Okay, now GPT-3 is working with the matrix of 2048 for its context maintenance. Okay, not GPT-3, the old versions of GPT. That's why when if you see when you are making use of old versions of GPT, you are doing conversation with it. But after some time, you will see that, oh, I told it already. No, in the first step itself. Why did it miss it? Because it didn't maintain that much of context. As the models and versions are increasing, the context window it's increasing, and now we can do a lengthy conversation. But this is what the context is all about. So yeah, I'll hold on my horses now and I'll talk all these topics in the coming sessions. So I hope as part of our LLM overview, your LLM basics, transformer architecture, tokenization and embedding is clear. And in the next session, we are going to learn about the attention before we go to the next pieces. Okay. I hope that you like the session, and if you want me to simplify anything else or you want me to cover anything else that I missed in today's thing, do mention in the comment section. Hope you like the session. I will keep the GitHub link where you'll find this deck, the Jupyter notebooks, and everything. That's all for today. Thanks a lot. Let's meet in the attention session. Yeah, let's meet in the attention session with full attention. Thank you. Forgot to mention, do subscribe, like, and share. And you can follow me on my Insta channel. You'll find the link somewhere here on in my bio. And with that mention, thank you all. Forgot to mention, do subscribe, like, and share. And you can follow me on my Insta channel. You'll find the link somewhere here on in my bio. And with that mention, thank you all.